So I'm going to cover the use case, so the model and the data set I'm using for this example. I'm going to discuss at length the implementation, so how we actually did it, and then I'll show some example results and open the floor for discussion. So the use case, we're going to do a generative model for sentiment analysis. We're going to be using a model and data set from Hugging Face. For one, this is an example, so we want to show a very common use case that our customers use. Hugging Face is everywhere, right? But what I show you, as I said earlier, will apply to any model you would ever bring to SambaNova, no matter the size, the scale, or the type. It's the same process for each. And the model I'm using is from Hugging Face. So I'm using GPT-2, and I'm using the SST2 dataset, which is movie reviews. Nothing too complicated, but good enough for an example. So this model, this process, I'm going to break it down to two parts. The first will be training a model, fine-tuning on the SST2 dataset. I'm going to extract those weights as a checkpoint, and then I'm going to apply that checkpoint to a model for generation. So a model that will actually make the inferences. So we're going to be using two models here. So the basic setup, this is similar to what we had yesterday. First, you're going to configure your input arguments for compilation running. You're going to create dummy inputs for graph tracing. You're going to prepare your input data. So any LLM, just as any other model, will expect certain types of input with specific shapes of the tensors. And in the case of a GPT-2 model, in addition to the raw data, it'll expect things like position IDs, labels, which are just the input IDs shifted over by one, and target token type IDs. So what exactly it's going to be predicting, its targets. You will then create data loaders, over your tensors so that you can bring your data in. You'll define your optimizers, so how you're going to actually make your model learn. You'll define your training loop. And we'll also define an evaluation loop in this example. An evaluation loop is not strictly necessary, right? You don't need to do it, but it is a good way of sanity checking your model in any environment. As part of that training loop, we'll also convert our torch tensors to Samba tensors. We'll convert the model graph from torch to Samba. We'll compile that model so I can run an RDU. We will run the model to train it, and then we will deploy it so that it can be inferred with. So we saw this yesterday. These are input arguments. These are the common ones, the ones that can be used for run, the training, or for compilation. And these are defined in your Samba code. So as I said, I mentioned that we extend the Python arg parser with a SambaFlow version. And you would just define functions in your code that provide these command line arguments. And you'll see we define several here, right? So you can bring in a model name. So from GPT, so you can bring GPT-2 from Hugging Face. We define a config name. So, with Hugging Face or with any model, you can find a config. So there's a default for GPT-2, or you can give your own config and override that. A cache directory for saving artifacts, a max sequence length. So of course, this is really important for any sort of LLM, is what is the length of the sequence you want to work with. So that's going to be key. And then we have things like weight decay. So we're going to be using Atom W to give you a little preview of the optimizer we're using. We define a grad normalization clip. So, you cut it off, make sure it doesn't explode. A learning rate, standard stuff, dropout rate, and loss weights. So that's relative weight of the tokens for the prompt. Now, we define these for how we're using the GPT-2 model. For any given model, right, the model will expect certain parameters, certain values. So you would define those yourself, right? You know the model, the data, so you would be able to define the inputs that the model would expect. And these arguments for input are just for training. They're for when you run the model. So we define a data directory. So where exactly are we pulling the data from? The number of steps to train for. In our case, we default to 800, but it can be any number. We also define a minimum evaluation accuracy. So this isn't part of a model, It's just a way of setting a minimum standard for what we expect it actually to be. And you'll see that value when we define the actual argument, the actual commands to run things. We define the subsample evaluation portion. So how much of our data should be used as evaluation. And then the checkpoint name. So where are we pulling in the checkpoint from, if any at all, right? We don't have to, but in this case, we will be doing so. And as yesterday, we need to create dummy inputs. So for compilation, this should look somewhat familiar, right? So we have our input IDs from the data. Now, again, when we're doing dummy inputs, it's the shape that matters, not the actual contents. So our definition of input IDs is just based off of the shape of the data, right? That's all it is. And then we convert that to a Samba tensor with a from torch tensor call. And then we do that for the position IDs, the labels, and we return those tracing inputs. So one thing to note here is that the input IDs are in the data. Those are what's inside the data. The position ID and labels, so position IDs aren't actually in the data. We define those. And this is something that's sort of special about large language models, is that you have your raw data, but to use a transformer upon them, you need to add in additional details. Things that the model needs, for example, position IDs, attention masks, things like that. So that's what we're doing here, is that we're adding the shapes of all the tensors we will need to train and use our GPT-2 model. Now we're going to actually go about preparing the inputs themselves. So we have our actual data, so we need to define them. We need to prepare them to be used. And so what this function does, prepare inputs, is it creates position IDs, labels, target token type IDs, which will all be used by the model to train. While they're not necessarily part of the data set, we created them for training. The shape and values within these will depend on the data. So you will have to be aware of your data set, what's inside it, what things look like, and what your model expects. And ultimately, the output of the tensors here, so you see the return trace inputs, these will be the same shape as the dummy inputs we just defined, right? They have to match. Okay. And we covered this yesterday, but a Samba tensor is just a wrapper around a torch tensor. And here we're saying get runtime inputs. So this is the input from the actual data set. So we're getting the inputs to train from a data loader. So we pull them in, we pull in the input IDs, the attention mask, position IDs, labels from the torch input, and we convert them into Samba tensors, to make sure that they can work. And we didn't see this earlier, but the attention mask is critical for an LLM, in that it tells the model what to pay attention to, what to attend to. So you need to make sure that that is very clearly defined, which we do here. And then we have to do our data loading, and this is something that we saw yesterday. And the difference now is that what we're doing is we're wrapping up in a function. So we're going to get iterators over our data for the training data set, so that we can train per epoch. And something you will note is that we take in the data, and then we are doing something called pre-training generative data set. And this is a Samba flow object. It's something that we have, and it just turns your raw data file into a torch data set, which can then be turned into a torch data loader. I'll show an example of that in the next slide. With that training data, we then create a sampler. In this case, a random sampler. We want to pull random tensors. We don't want to, be stuck with just the same set over and over again. And then we create the data loader. And we will create a data loader for each file in the data set. So we can read all the data that we need for any given number of files, for any given size of file. It's just a way of simplifying things for us. And then we'll also load data for evaluation. So it's the same process. So the one difference here is that we check that our subsample evaluation set is larger than 0 and smaller than 1, right? It needs to be in that range. You can't use all the data for evaluation. So, we do that check. Not necessary, but it's just for sanity's purposes. We then choose the files we want to sample. We choose it from the full data set. And then using the same process, we create those data loaders over those data files, and we return those data loaders. One thing to note is that we do set drop last equals true. So what that means is that if your data set isn't evenly divisible by your batch size, then the remainder of samples will just be ignored. They'll be dropped. What this lets us do is it lets us avoid padding on the batch dimension. And padding the tensor is usually, it's okay. It's very common to do with large language models. But generally, you don't want to pad on the batch dimension. So that just gives you a bunch of 0, length batch sizes. So we just drop those extra batches and keeps the code clean. And this is the pre-training generated data set that I mentioned earlier. So it reads in this case, it reads in an H5 file. It sets up the keys and sets up the data set. So it's really just an extension of TorchUtil's data set. All we're doing is we're just extending it a bit so that it can work, in SambaFlow. You'll see that we define the len and get item, dunder methods, so things all work fine. So, okay, Scott, I see your question in the chat. The return type should be a Samba tensor. Ultimately, is what you're going to get. So what you're going to get out of the data loader, of course, is torch tensors. But what you want to give to Samba is the Samba tensor. So you would call a from torch tensor on the output of your torch data loader. Or, as I mentioned yesterday, you could wrap your data loader in a Samba loader, and that will just do it for you automatically. We're doing it with the data loader in this example, just to show you the low level, right? The underpinnings. We don't want to hide anything while you're learning. And now the optimizers. So SambaFlow has built-in optimizers. We have AtomW and SGD. You can bring in your own, of course, you can define your own. But in general, AtomW is a very common optimizer for large language models. Provides good coverage, or convergence, I mean, and works very stably. It's especially common in Hugging Face models. So expect it as you learn more about large language models. And here you'll see we're actually defining 3. We're defining one for the embedding dimension. We're defining an optimizer with weight decay and one without weight decay. So in the case of without weight decay, our AtomW turns into just plain atom, actually. And these will be used to go over the tensors we're training in the model. And we return a tuple, or a list actually, of the 3 optimizers. And we will iterate over those as we iterate through the model and train it. We'll see that in the training loop. Okay. And now the actual model step. So this isn't strictly necessary. You don't have to define a model step function, but we did this to keep our training loop simpler, right? The training loop can get, you've seen them, they can get rather long. So for the part that relies explicitly on the RDU, right, the samba.session.run, we just broke that away into its own function just to make it easier to read. So, what it does is it brings in the model, brings in the inputs. It it sets up the learning rate, dropout rate, hyperparameter dictionary that I mentioned earlier, as well as a dropout dictionary. These are things that can change on a schedule. So we pass them in as arguments that can be modified during runtime via the hyperparameter dictionary. The loss scale. So depending on the labels, the scale, the loss scale can change. So we define a function that allows that to be adjusted per input, depending on the padding and what's ignored during that step. We then set up a couple lists to capture gradients and the inputs we want to run, just to be able to track them and feed them in. We then call our get runtime inputs function to get the inputs for this particular step. And we add those to our lists. And then you'll see that we set our SN grad to loss scale just before the run call. So what we're doing here is that SN grad is a tensor that stores the gradients on RDU. So we're initializing them to loss scale so that as you update them, they get automatically added to the gradients. And then we call the run. So we call run on the inputs for this step. We use the traced outputs, right? So that the outputs we get from the compile, right? That dummy stuff. We put in the hyperparameter dictionary, and then we define the section types we want to run on RDU. Now, if you had included this section types argument in the function, it would have by default run all of the sections, right? That's default. We're just calling it out here. So you'll see that we're running the forward, the backward, the gradient normalization, and the optimizer sections all in RDU. And of course, as I mentioned earlier, you can run different sections at different times. You don't all have to be simultaneous. Then we gather our Samba losses, the actual losses from that function. And in general, the outputs of the run function, I mentioned this yesterday, will be the outputs of your forward, right? The forward of your model is what defines your outputs. And as a general rule, the first element of your outputs should be your loss or your logits. It should be the values that you actually want from the forward. Just makes them easier to grab for future work. In this case, to compute things like loss or evaluation. So we take that, we apply 2torch to it, so that it goes back to torch tensors, so that we can then apply the loss scale to our loss. And then we sum over it to get our full loss for this step. And this defines just one step of the model. And there'll be, of course, many steps defined by the number of epochs, the number of steps you define to run training for. Excuse me. And now the training loop. Now, you'll see that it is kind of long, but imagine if I included the model step code in this, it'd be even longer, much harder to read. So this makes it a bit simpler. So it consists of 3 loops. The outermost is a while loop, and it just checks for completion. And that's based on the number of training steps you defined in the command you give. So in our case, we're going to be doing 800 steps. So this will loop over at least 800 times. So what it does, it will set up the training data loaders. And when the training completes, those inner loops for training complete, it will then call the evaluate function, which we'll go over in a little bit, to actually evaluate your results to see how your model is performing. The innermost loop, that's what actually iterates over the batches from the data loaders. And it is that second inner loop that actually loops over your batches. So it goes over your batches, feeds them into the inner loop, which actually calls the model step. And the model step trains on those batches, gives the loss back, which just repeats the loop over and over and over again. We do regularly check for what step we're on to make sure we're still, below our maximum training limit. And you'll see we're tracking various things. So for example, one of the reasons why we're using Hugging Face in this example is that when you do use Hugging Face, is that Hugging Face just gives you automatically with any given model tokenizers. So we leverage that in this example. We track evaluation loss, epochs we're on, post steps taken, and you'll see that when we take the step, we track the loss values added to the list, so we can track everything. You'll notice in the code that we have a p-bar, so we're using TQDM in our example here, just to have a little progress bar, so that shows up on the command line. Not required at all, but it can make things easier to read for yourself and for your users. And you'll see once you come out of that, we then call evaluate. So give it the arguments, the model, the trace outputs, and then we evaluate the model's results based off of what it was trained on versus the evaluation subset. We do assert that that the evaluation accuracy be greater than whatever minimum evaluation actually we defined in the command line arguments. By default, that's just 0. So it's a low bar for this model example. But if you expect a certain level of accuracy from any model you might run, this would be the way to enforce that. Then at the very end, we save the checkpoint. And I'll show you that code in a little bit too, what that save checkpoint looks like. But basically what it amounts to is you take your tensors, your Samba tensors, you export them out to torch tensors, and then you can just call save on them like you would in normal PyTorch. And now evaluation. So the evaluation, it should look very similar to what we've seen before. It's almost line for line a copy of the training loop. It differs in that one, it calls the get eval iterators function. So we want to iterate over our eval data, not our training data. The outer loop iterates over the data loaders. Then the next inner loop goes over the batches from each data loader, prepares the inputs, gets runtime inputs, calls the run, and it saves the logits. So something to note in the section types is that when you're evaluating, you're running effectively an inference, right? You're not actually training anything. So in this case, we're only going to run the forward section. So you'll see here that we only pass in section types forward because we're only looking to evaluate. We're not looking to train. And in this case, our logits from what we've returned from the forward, those are in the first position or the second position. So we capture those. And then we go and we start making our prediction. For each sample in that range of the batch size, we check the targets. If it matches the sample, we get the logit of that sample, and then we make the prediction. Towards our argmax of the logits on the axis that we expect. And that gives us the result from this particular evaluation based on our trained model. We track that. We make sure that it's not a completion token data type, so that we're not at the end. We check for that. And for any given label, we track it, and for any given prediction on that label, we track that too, side by side. And then based off of those lists, we'll compute our loss scale, right? So we can make sure everything's matching appropriately to what we had in training. And then we will call this at the very end of that, the exact match accuracy function. And this is just a little helper function, and it just compares those two label and prediction lists to see how they match up to determine your accuracy and valuation. And then this function just gives you back the actual eval accuracy as well as the total eval loss. Okay, now we're going to tie that all together, and we're just going to put that into a typical main function that you see in any Python program. So I mentioned this before, that we extend the arg parser. So we have a function built into SambaNova called parse app args. And what you would do is that you would pass in your arguments to this parser function. So we pass in argv. So this is your Python compile, Python run section of the command. You pass in the common parsers. So that was that first function I showed you. And then we pass in the run parser arguments, which was that other parser function I showed. And we pass those in as Lambda functions. And now SambaFlow has all the arguments you would want or you expect for your models within it. Okay. And then this next section, that's the actual Hugging Face connection. So if you provide a model name or path, well, then the model will be called with the AutoModel for causal LLM, not from pre-trained. And that will pull in the GPT-2 model from Hugging Face that matches what we have in our config. And then we set training to true. And if we provide a config name, without a model name, then we will set up a GPT-2 model with our config file. And I'll show an example of a config in a few slides. And that's really all you would need from Hugging Face. Now this section, say you weren't using Hugging Face, say you had your own model, you have your own LLM, whatever that might be, and you want to use, SambaFlow for it. Well, in this case, you get rid of this Hugging Face section, and you would just call compile and run on your model, right? So you'd make sure that your model was prepped for SambaFlow, right? You'd make sure that you had all the, tensors defined, all the nested things mapped out, the dummy tensors, all the things we mentioned before. And you would just call this on your model. There's nothing here other than the direct calls to Hugging Face, those 10 or so lines. That's it. That's all that's Hugging Face is in here. Everything else is general PyTorch and SambaFlow. So what I'm showing you here can apply to whatever model you'd like to build. Okay. One thing I have to call out here, though, that is specific to SambaFlow that isn't strictly necessary, but is helpful, is this patch model function. So what we found when using Hugging Face is that some functions don't perform as well in RDU as we would like. So what we've done is we've created patch functions over those Hugging Face functions to make things run better on RDU. They aren't needed, right? You could compile and run the model without them, but they can help with performance if you're using a Hugging Face model. I'll show you a little snippet of the patch model, what that looks like in a bit. Excuse me. But just want to give you a heads up about that. Then once you have all that done, you of course convert your model. So the from torch model underscore, and that'll take your model from torch to Samba, convert all your parameters. Next up, we get our compile inputs. So we want to make sure we have our dummies, right, our dummy inputs. Get our optimizers for the model. And then, of course, we check for the command we're getting. So if it's a compile, well, we call session.compile, and we pass in the model, the inputs, optimizers, output grad initialization, and whether or not this is inference. And I'll show you that when we do generation. But there is a flag, a command flag, -- inference, which is what you would use to set up an inference model. By default, it's just false if it's not included. And then finally, you'd call run on a compiled model. And as I mentioned yesterday, when you call the run, first thing you do is you trace your graph, right? So you tell that trace graph, and then you call that on your models, inputs, optimizers, your PEF, and you'll get out your traced outputs. So you can feed that into your model. And then you call train, and that calls our training loop, which calls our model step. And this is what you do for literally any model you want to bring onto SambaFlow. Not just LLMs, but if you want to bring on vision models, you want to bring on some esoteric model that you built by hand, that's something totally different, it'd be the same methodology. Okay. And this is the patch model. So what we do is that we call this helper, and we call it with a certain arguments. to replace certain functions. So you'll see in the GPT-2 patch helper, so we set the model forward to the GPT-2 head forward, and we replace it with, and we set up the get, the get under method. And then within that model, we then replace and extend various layers. We change some of their parameters, just so that they perform a bit better on RDU. If you are using LLM and you are having an issue with performance, and you open up a support ticket with us, this will be one of the things that we would look at. Is, okay, what model are you using? Oh, you're using Hugging Face? Okay, so let's take a look at that model and see if maybe we can patch it, and see if we can maybe replace functions in it so that it can perform better on RDU. Now, of course, this isn't required. There are other ways that we can optimize the model, but this is one method. And I just wanted to make you all aware of it, that this is something that one of the things that we can do to help make a Hugging Face model perform better on RDU. And not every model will need it. It will depend on the model itself. And then I did mention like helper functions. So exact match accuracy. As you can see from the definition, it's literally just comparing the label and prediction lists I mentioned from the evaluation function. And it just sees that if they match, and if they do, then that's a correct prediction. And you just count that towards the accuracy improvement. And that's all that does. Just a simple helper function, not necessary and not part of anything. It's not part of Torch, it's not part of Hugging Face, not part of SambaFlow. It's just this helper function. And save checkpoint and load checkpoint. And oh, I'll have to fix the screenshot. I apologize for the tooltip. But it takes the session, the save checkpoint, and it puts it all to CPU. So it does it to the entire model, to CPU on the model. And that gets all the parameters, all the weights out of the model, and takes them from Samba tensors to Torch tensors again. And then it extracts the state dictionary from that Torch model now, iterates over them, grab all the keys and values and items, and then it just calls a torch.save on that information. And load checkpoint does the reverse. So when I said yesterday that anything that you make in SambaFlow will ultimately work on a CPU or GPU, this is what I meant. We don't lock you in that way. If you want your data out, you want your weights out, your parameters out, just call toCPU on any parameter, and it's now a pure Torch parameter. And you can do whatever you want with it. You can save it, you can manipulate it, whatever you so choose. You could take this checkpoint to anywhere you'd like. So long as wherever you're taking it expects those data types, it's all good. And these are the compile and train commands for training this model. So we call compile. We give it the maximum sequence length, the batch size we expect. We give it the path to a config file if necessary. We pass in things like weight decay, grad norm, the model name, GPT-2 in this case. How many tiles we want to use, and this is something that Bruni talked about yesterday when she was talking about how to actually use the scheduler Slurm, and you give it the name of a path. And by default, SambaFlow will put the path in the same directory that you ran the command from, and it'll put it under a directory called out. So it'll be out / your path name, and then all the artifacts from that. And then the training command is very similar. So same sequence length, same batch size, same weight decay. Differences would be you include the data directory now, where the data is that you're going to train on. If you're going to use checkpoint, you'd pass in checkpoint name here, and that's where it will output your weights to. You define the number of steps. So, in this example, when I show you the results at the end of the presentation, it's for 800 steps. And And of course, you have to pass the PEF, where the actual binary file is that needs to be programmed onto the RDU. And we do use minute value accuracy. When I did this example, I defined it to be 0.87. For this case, for this model, that's kind of arbitrary. It's not a complex model or a complex use case. So this is just as an example of what that would look like. And then this is the config file. And see here, I see a question from you, Bill. Is num tiles required? Yes. For your SN30s, you have to define the number of tiles you want to deploy to. So you're compiling for 4 or 8 in the case of a full socket, what have you. So you have to specify that. Can we transfer the model back to PyTorch Hugging Face for inference? Yes. So as I said, you can take the weights out of the model as a checkpoint and take them anywhere you want. So when you take them out of, Samba, they just become torch sensors. So you want to make sure that the data types are good. So MP32, BF16, you want to make sure that they match, what you expect. But they're just torch tensors, so they can be used anywhere that can run torch. Okay, and this is the config file. And this config file, if you passed it in during the compile or training, it would overwrite or overtake the config from Hugging Face. So activation function, architecture, and all the various arguments you could set. So residual p drop, number of positions, number of layers, number of heads, initialization range, the epsilon of your layer norm. These are all things that you could change here. And we would pass those along to Hugging Face, and Hugging Face would give us back the model that matches that with those values. Okay. So I know that was a mouthful and I dumped a lot onto you, but we'll move on to generation. And generation looks very, very, very similar to what we did for the training portion. You'll see the same sort of commands, same sort of structures. It's just that now we're geared towards, inference rather than training. Excuse me. So again, the basic setup is very similar to training, and that's on purpose. There was no need for us to make inference look any different from training, right? You change a few of your arguments. You focus on your forward, not your entire pipeline, but that's really it. So configure your input arguments, create your dummy inputs. The generative model is inference, so we're not actually training the model. We're going to actually just take our checkpoint, that we got during training, and we're just going to apply it directly to our inference model. Now, it does need to be compiled. For SambaNova, any model that's going to run on our platform, be it for training, fine-tuning, inference, it needs to be compiled. If it's not compiled, there's no binary. If there's no binary PEF, then it can't be deployed onto RD. So, we're going to compile it. The weights, they come from that checkpoint. So we're just going to load them right in. We'll do our conversion from torch model to Samba, and we'll compile the model, to run on RDU, and then we'll run the model on RDU to get those predictions. And this sort of lines up with your question, Pedram. You'll see that I say convert the model graph from torch to Samba after I say load in your weights. So the thing is that when you save the checkpoint out, you're saving torch tensors. They're just pure torch. So when you apply them to the model, well, the model will then have to be converted from torch tensors to Samba tensors. So again, when you save a checkpoint, it's just tensors. Use them anywhere. And then here are the input arguments. It is a smaller list, because we're just doing inference. There's less to do. We're not actually doing any hardcore training. The one I want to point out is just that we have an argument here in the common args for how many examples to generate. So it can be any number. You can generate just one, or you generate 100. It would just depend on what you like from your output. And then for run arg, when we run it, we give it the data directory, then we give it the checkpoint directory. So it can build itself. And again, we define our dummy inputs. Shape matters, actual data doesn't. But you'll see that it's pretty much just the exact same function. We define our input IDs, position IDs, the attention mask, and that's what we're tracking. That's what we need. And these all get converted into Samba tensors. We call it prepare inputs, which again is very similar to what we had for training. We create our input IDs, attention masks, and we create our position IDs. These are all then converted to Samba tensors. And then we call the generate function. So this is similar to the evaluation function we ran previously. So at the beginning, we load our checkpoint. We get those weights. We then define a small RDU step, right? So again, it's only the forward, because we're just doing inference here, so we don't need the whole thing. And we're capturing the logits in this case. And the key thing to note here, and this is something that we've done just because it's Hugging Face, is that this model RDU step, we're going to use it to overwrite the model's original forward. So you'll see here we call base model class, model dunder class. So what we're doing is that we are replacing the call of the Hugging Face GPT-2 model with our model RDU step. So whenever the Hugging Face model gets called whenever its forward gets called, what it'll instead call is our RDU step. And that's why our model step here returns an actual Hugging Face object. So it returns a causal LM output with cross attentions. Now, this isn't necessary. You don't have to do it this way. But this just shows what you can do with, with knowledge of the model and its structure. This simplifies things. It means that when you call the Hugging Face model on an RDU, in this case, it will automatically call the forward that is part of the definition on SambaFlow. Or you could call it and just convert it automatically with Samba tensor from torch model. You can convert it that way too. So we do that here, and then we do use a tokenizer for Hugging Face. So we use the one associated with GPT. And then this is a generative data set. So this is another functionality that SambaFlow provides. And I'll show you the definition in a little bit. But it will create a data set out of the original files. And then we just go over the data set. So we go over it, we go over the examples, and then we tokenize using the tokenizer for each prompt. And our return tensors are torch, so PT. We get our input IDs, our input length, and then we feed them into the model. So GPT-2 from Hugging Face, we call generate on it. And this generate will call, because we overrode it, it'll call the actual RDU steps. And so without having to open up Hugging Face, without having to doing sort of like conversions in that code base, we just replace it so that when you call the generate function from that model from Hugging Face, it just calls our stuff. So it automatically converts it into SambaFlow. And then we use that generated IDs to generate text. And those will be our sentiments. It'll be positive or negative, what have you. And then, of course, we return those predictions. So again, we have a patch. So, it's the same sort of patch, but This is what that is again, just to emphasize it. And then we pull all together in the main. And again, this looks, very, very similar to our previous main. One key difference is at the very end, we just pull out the predictions that we get back from our generate function. And so that gives us back, whether for any given prompt is the sentiment positive or negative. Compound first commands, again, they look very, very similar to the previous ones. Key difference is that, we now pass in the inference flag, and that's true. So that lets SambaFlow know that, oh, okay, we're running inference now. So it captures that flag and adjusts. And then here are some results, positive and negative. Like, I love his martial arts style. It is quick, close up. And if you read that, it comes out overall, though, that it was negative. He says the movie suffered. Okay. So any questions? That's the presentation. And we're, I think, just about at time, actually.